Hey there, let's talk about wave motion and sound. I remember staring at this chapter in my physics book for what felt like hours, reading the same page over and over, and it wouldn't click. If you've ever felt that way, you're in the right place. Today, we're going to make this make sense for good.
I mean, seriously, why are they so confusing? You open the book and you're hit with these squiggly lines and a bunch of jargon like propagation and oscillation without any real-world context. It all feels so abstract, right? And they just expect you to perfectly visualize this invisible motion in your head. It's a really tough way to learn. So, here's our plan. We're going to tackle this step by step. First, we'll talk about why it's so confusing. Then, we'll uncover the one simple secret to understanding what a wave really is. After that, we'll look at the two main types, learn to speak the language of waves, and finally, see how sound actually gets from point A to point B. It's going to be a clear path, I promise.
Okay, let's just dive right in. The main reason this gets so confusing is that textbooks just throw all the math and the big words at you from the get-go, They don't build that basic intuition first. You get hit with wavelength, amplitude, and frequency all at once, and it's so easy to get them all mixed up.
And here's the thing, this is the root of the problem. They just assume you can magically picture these invisible forces. But that's not how our brains work best, right? We need to connect ideas to something we can actually see and feel. So that's what we're going to do. We're throwing out the old way, and we're going to build this up from the ground, using examples you can actually picture.
All right, let's get to the good stuff. It is time to reveal the big secret about waves. And you know what's great? It has absolutely nothing to do with complicated formulas. Not yet, anyway.
Just imagine this for a second. You're holding one end of a long rope. You flick your wrist up and down, just once. You see that hump, that wave, travel all the way down the rope. Now, here's the crucial part. Look at that little piece of ribbon tied to the rope. It just bobs up and down in place. It doesn't travel with the wave. The rope didn't fly across the room, did it? Only the disturbance, the energy from your flick, traveled forward.
And that, right there, that's the definition of a wave. It is not the movement of stuff, it is the movement of energy through stuff. The medium, whether it's the rope or water or the air, it pretty much stays put. It's just passing the energy along, like a baton in a relay race. Let me say that again, because it's the most important idea. A wave is the transfer of energy, not the transfer of matter.
And you see this everywhere once you start looking for it. Think about a wave at a stadium. People stand up and sit down, but they don't actually run around the stadium, right? They're the medium. The wave is the disturbance moving through them. Or ripples on a pond. A leaf on the water will just bob up and down. The water itself isn't flowing outwards. It's this beautiful, simple concept.
So now that we know what a wave is, a transfer of energy, let's check out the two main flavors they come in. This is another one of those spots where textbooks can get confusing, but I've got a super simple trick so you'll never mix them up again.
Okay, look carefully. On the left, we've got transverse waves. This is where the particles of the medium move perpendicular, or at a right angle, to the direction the wave is going. Think of our rope again. Your hand moved up and down, but the wave moved forward. Here's the trick. Think of the letter T in transverse. It stands up tall, just like that up and down motion. Now look at longitudinal waves on the right. Here, the particles just shuffle back and forth, parallel to the wave's direction. Think of the letter L for longitudinal, lying down, just like that back and forth motion.
And this is absolutely critical. You have to remember this one. Sound is a longitudinal wave. When you talk, you're literally pushing air particles together and then letting them spread apart, and that compression travels forward, in the same direction you're speaking. This comes up on tests all the time, so really lock this one away.
All right, it's time to learn the language of waves. We're going to tackle those three big words, wavelength, amplitude, and frequency. They might sound a bit alike, but they describe three totally different things about a wave. Let's break them down, one by one, nice and easy.
First up, wavelength. This one is exactly what it sounds like. Imagine you take a snapshot of a wave, just freezing it in time. The wavelength is simply the physical distance from the peak of one wave to the peak of the very next one. It's a measure of length, how long one full wave is.
Next, we have amplitude. Amplitude is all about energy or intensity. It's just a measure of how high the wave gets from its center resting point. And here's the crucial connection you need to make. For sound, amplitude is loudness. A wave with a really big amplitude, that's a loud, booming sound. A wave with a tiny amplitude, that's a quiet whisper. It's that direct. And finally, frequency. This one's all about timing. If you stood in one spot and counted how many complete waves passed by you in 1 second, you'd be measuring the frequency. For sound, frequency gives us pitch. A high frequency, lots of waves passing by every second, is a high-pitched sound, like a flute. A low frequency, fewer waves per second, is a low-pitched sound, like a deep drum.
Okay, so let's put this all together and talk about how fast sound travels. And the answer isn't just one number. It completely depends on what the sound wave is moving through.
As a baseline, in the air around us, sound travels at about 340 meters per second. Now that's pretty fast, but it is way, way slower than the speed of light. And that's exactly why, during a storm, you always see the flash of lightning before you hear the boom of thunder.
But check this out. Look at what happens when we change the medium. In water, sound travels more than 4 times faster than in air. And in solid steel, it's over 14 times faster. So why is that? Well, think about it. The particles in liquids and solids are packed way closer together, so they can pass that vibration, that energy, from one to the next much more efficiently and quickly.
And that brings us to a classic question. Why in all those sci-fi movies, when a spaceship explodes, should it actually be completely silent? Well, the answer goes right back to that fundamental secret we learned. Sound needs a medium. It needs particles to vibrate. Space is a vacuum. It's empty. There are no particles to carry the vibration. So no medium, no sound. It really is that simple.
So what can you do to really make this stick? I've got a simple 3-step plan for you. First, just try to draw both kinds of waves from memory. Can you show how the particles move? If you can, you've got it. Second, do a few practice problems with the main formula. And third, and this is a big one, make a little chart that connects amplitude to loudness and frequency to pitch. Do those 3 things and you will own this topic. And here it is, everything we've talked about, all in one place, your cheat sheet. A wave is just moving energy. Transverse is perpendicular motion, think T. Longitudinal is parallel motion, think L. Amplitude is loudness. Frequency is pitch. And sound absolutely needs a medium to travel. These are the big ideas. Think about where we started, with confusing lines on a page. And now you have a clear mental picture of what a sound wave actually is and how it moves. So my question for you is this. Now that you've seen how powerful it is to visualize something, what other invisible physics concept, like maybe gravity or electricity, would you like to see explained in this same simple way? Thanks for watching.